Okay, hello everyone. So let us now proceed to the fundamental set of solutions and then the general solution of homogeneous equations. Okay, so in this lesson, we will go through the definitions and then finally we will have an example here of how to construct the general solution of a homogeneous equation. So we will be using the concepts that we've learned before and we will be applying it here. Okay, so let's start with the fundamental set of solutions. So any set n, any set of n linearly independent solutions. So linearly independent, as you can see here. So the topic linear independence is significant here, right? Of a homogeneous linear nth order differential equation on an interval I is known as the fundamental set of solutions. Okay, the existence of such a set is answered by the following theorem. So there's a theorem which states that there exists a fundamental set of solutions for the homogeneous linear nth order differential equation on an interval I. So we have this fundamental set of solution. Okay, so as you can see here, it is important to determine if it is linearly independent. Okay, linearly independent solutions, and then if it is an nth order differential equation, then there are n linearly independent solutions. So I've listed out some pointers later on that we will use for the example. So let's just proceed for now to the general definition of the general solution. Okay, let's go to the definition. We have here, let y1, y2 up until yn be a fundamental set of solutions. Okay, so fundamental set of solutions of a homogeneous linear nth order differential equation on an interval I. Okay, so y1, y2, and yn is a group of functions that are linearly independent. Okay, that are solutions to the homogeneous linear nth order differential equation. Now the general solution, so this is the part where we construct the general solution, is equal on the interval is this. So y is equal to c1 y1 of x plus c2 y2 of x plus cn yn of x. So what can we recall about this? So this is the linear combination of the fundamental set of solutions, right? Of the functions inside the fundamental set of solutions. So we've already discussed a linear combination as well. And where I is equal to 1, 2, and are arbitrary constants. Okay, so let's take a look at the 3 points. So in order to verify a general solution of differential equation, so let us keep in mind these 3 points. Okay, the number of solutions should be equal to the order of the equation. Okay, for example, if the equation is second order, there should be 2 solutions. Okay, that is our first step. We should count how many solutions there are. So in this part of the lesson, so we don't know the techniques yet in order to determine the solutions of nth order differential equations. But in this example, so we are given the solutions as from the start. Okay, but later on we will know how to get these solutions. And for the second one, the given solutions should satisfy the differential equation. So we will check that also, that all of them satisfy the differential equation. And then the last one will be the solutions should be linearly independent. Okay, so let's make this concrete by doing an example. Okay, so as you can see here, let's do example 5. So verify if the functions y1 is equal to e raised to 3x and y2 is equal to e raised to negative 3x form a fundamental set of solutions to the equation y double prime minus 9y on the interval negative infinity to positive infinity. Then construct the general solution. Okay, so let's take a look. The first key point is that the number of solutions should be equal to the order of the equation. So what is the order of the equation? So order of our equation is second order, right? You can see here it's second order. And how many solutions do we have? We have two. Okay, so the first key point is satisfied. Okay, so we are good with that. So how about the second one? So the given solutions should satisfy the differential equation. Okay, they should satisfy. So how do we check that? Okay, so let's check one by one. Let's use the first solution using y1 is equal to y is equal to e raised to 3x. Okay, so let's get the first derivative. That would be 3 e raised to 3x, and then the second derivative is 9 e raised to 3x, right? Okay, so now that we have this, let's substitute. Substituting to the differential equation, we have y double prime. Y double prime is 9 e raised to 3x and minus 9 multiplied by y, which is e raised to 3x, equal to 0. So this is clearly equal to 0. So therefore, we can say that this first solution does indeed satisfy the differential equation. Okay, so let us do the second one. So let's do the second one. So using y is equal to e raised to negative 3x. So y prime is equal to negative 3 e raised to negative 3x, and double prime is 9 e raised to negative 3x. So let's try. So we have substituting y double prime 9 e raised to negative 3x, then minus 9 times e raised to, or y is e raised to negative 3x. So this indeed again is 0. Okay, so we can say that the second solution is also is indeed a solution. So it satisfies the differential equation. Okay, so now that we verified that, so we can say that the second key point is satisfied. Now the third one, the solution should be linearly independent. Okay, so here is when we will use the Wronskian, or you can also just observe if because some in this case you can see through observation that this is linearly independent, but it's good to make sure by using the Wronskian. Okay, so let's apply the Wronskian. So e raised to 3x, e raised to negative 3x. So how do we set up that? So e raised to 3x, e raised to negative 3x. So we set up a 2 by 2 matrix. So the first derivative will be 3 e raised to 3x, and then negative 3 e raised to negative 3x. Okay, so let's get the Wronskian for that, or the determinant of that matrix. Okay, so we will get e raised to 3x multiplied by negative e raised to 3x, then we will get negative 3 e raised to 0, right? Because we will add this e raised to 3 negative 3x plus 3x, so that will be e raised to 0, so this will be 1. Okay, and then we have minus, what do we have here? So we have here minus 3 multiplied by e raised to 0 again, right? Because the same thing happens, so you need to add 3x to negative 3x, so this is from the law of exponents, and this will be 1 also. So therefore, we will get negative 3 minus 3. Therefore, we will get negative 6. Okay, so what does this mean? So this means that no matter what x value we choose, um, the Wronskian will always be negative 6. So it is not 0. Therefore, this is linearly independent. Okay, so we have satisfied all of the three key points in order to verify if this indeed forms a fundamental set of solutions. So now that we've verified that, we can then construct our general solution. So from the definition, our general solution is of the form y is equal to c1y1 x plus c2 y2 of x. Okay, so let's do that. So c1, and what is our y1 is e raised to 3x plus c2, and our y2, y2 is e raised to negative 3x. Okay, so this is our general solution for this homogeneous linear nth order differential equation. Okay, so that's how you construct the general solution. That's it for this video. I hope you learned something, and thank you for watching. See you in the next video.